In late 2018, Elon Musk scrapped years of advanced carbon fiber development and announced he would build the world's most powerful rocket out of stainless steel, the same material used to make kitchen cookware, stadium railings, and water towers. The aerospace industry thought this was borderline absurd. SpaceX had been working toward this rocket since at least 2012, when it carried the name BFR, and the plan had always called for carbon fiber composites. Lockheed used them, Boeing used them, NASA used them. SpaceX had committed fully, hiring an industry specialist called Ascent Aerospace to build production tooling that arrived at the Port of Los Angeles in April 2018, carrying a price tag estimated at several to tens of millions of dollars. And then Musk visited the Boca Chica production facility, and what he found there changed everything. The carbon fiber team was losing the battle, fighting wrinkles in the sheets, bleeding time, bleeding money, falling behind a pace that would never get anyone to Mars. Musk walked out convinced that continuing down that path would kill the program entirely. Within weeks, he called his executive team together and proposed switching to stainless steel. The room pushed back hard, and for good reason. Steel is denser than carbon fiber, heavier than aluminum, and had not appeared in a rocket program since the Atlas ICBM in the 1950s, a program that had not ended well for the material. Musk admitted later in his January 2019 interview with Popular Mechanics that it took him quite a bit of effort to convince the team to go in that direction. What broke the skepticism was the numbers. Once the team ran the calculations for Starship's specific requirements, a fully reusable vehicle built to survive cryogenic fueling, hypersonic re-entry, and repeated launches, stainless steel stopped looking like a step backward and started looking like the only material that actually checked every box. December 2018 made it official, and by March 2019, SpaceX removed any doubt by physically demolishing the Port of Los Angeles facility and scrapping the entire carbon fiber tooling program. Years of work gone. At his September 2019 public presentation, Musk called the stainless steel decision likely the single best design decision he had ever made. Start with the number that makes everything else make sense. $3 per kilogram. That is what stainless steel costs as a raw material, sitting across the table from carbon fiber's true cost of nearly $200 per kilogram once manufacturing waste gets factored in. Carbon fiber starts at $135 per kilogram, but roughly 35% of the material ends up as unusable offcuts during cutting and shaping. Musk put it plainly, you cut the fabric and some of it you simply cannot use, and that waste alone drives the effective cost to nearly $200 per kilogram. At 65-1 on raw material cost alone, the math tilts hard towards steel before a single engineering advantage gets mentioned. Scale that up to vehicle level and the picture sharpens further. Musk estimated that a carbon fiber Starship upper stage, before engines or any other hardware, would carry a material bill of at least $15 million for the carbon fiber alone, while still weighing between 80 and 100 metric tons. For a program built around launching at high frequency and building many vehicles, that number does not work. Raw material cost is only one layer of the argument, and the physics layer is where stainless steel wins outright. Starship operates in two extreme temperature environments within a single mission, and most materials can handle one or the other, not both. The propellant tanks hold liquid methane at minus 161 degrees Celsius and liquid oxygen at minus 183 degrees Celsius on the way up. Then, during re-entry, the vehicle's exterior faces temperatures exceeding 1400 degrees Celsius. Carbon fiber composites top out at around 150 degrees Celsius under steady conditions, with brief excursions to perhaps 200 before losing structural integrity. Steel handles 1500 to 1600 degrees Fahrenheit, more than 4 times the thermal ceiling of composites. And that gap carries a consequence that reshapes the entire vehicle design. Because stainless steel survives re-entry heat, Starship's leeward side needs no heat shield at all, something physically impossible with composites. On the windward side, SpaceX developed a dual-layer stainless steel heat shield with micro-perforations that let water seep through and cool the surface by evaporation, a method called transpiration cooling, made possible only because the underlying material can take the heat. At cryogenic temperatures, the material delivers one more surprise. 300 series austenitic stainless steel actually gets stronger in the cold, with yield strength climbing roughly 50%, which meant engineers could use use thinner wall sections without sacrificing structural performance. The material performs better when the tanks are full. Charles Kuhlman, vice president of materials engineering at both SpaceX and Tesla and a PhD graduate of Northwestern University, led the alloy refinement that turned this into a proprietary edge. Early prototypes used 301 stainless steel. SpaceX then shifted to 304L for better cryogenic toughness, starting with the SN7 test tank, and later vehicles adopted a patented alloy designated 30X, costing just slightly above €3.60 per kilogram, optimized for both thermal performance and manufacturability, a small tweak with enough of a performance gain to justify the patent. Carbon fiber manufacturing runs slow by design, with high tooling costs, a narrow specialist labor pool, and prototype cycles measured in months. What stainless steel enabled showed up fast. From the December 2018 announcement to Starhopper's first tethered test hop in April 2019 took roughly 4 months, and the serial number prototype program that followed, where SpaceX built, tested, and sometimes explosively destroyed successive vehicles, ran at a pace no composite program could have absorbed financially. Steel fabrication and welding draw from a broad industrial workforce rather than a narrow community of aerospace composite specialists. And at Starbase, the result looked more like heavy industry than traditional aerospace. Fast iteration, physical prototypes built quickly, early failures treated as data rather than disasters. Starship SN15 delivered the clearest proof of that approach on May 5, 2021, becoming the first Starship prototype to complete a high-altitude flight and land intact, with each vehicle in the sequence carrying lessons from the one before it. Starship has now completed 11 test flights, and version 3 sits on the pad for Flight 12 in May 2026, carrying Raptor 3 engines and significant structural modifications. NASA has tied its Artemis 4 lunar landing mission in 2028 to Starship serving as the crewed lander, and SpaceX is working toward FAA approval for up to 25 launches per year, backed by a new Gigabay facility designed to house at least 24 vehicle workstations at once. None of that scaling trajectory separates from the material at the center of it. When Musk sat down with Popular Mechanics in January 2019 and explained why he was building the most ambitious rocket in history from an alloy found in kitchen appliances, the answer came down to this. Carbon fiber costs nearly $200 per kilogram of usable material. Stainless steel costs $3. Steel outperforms composites at the temperatures Starship actually operates at, and the workforce to build with it already exists across global industry. What the aerospace world read as a step backward turned out to be a first principles answer to what aerospace materials are actually for: